and I'm happy to invite Gergo Igneczi from ISTRC21 University. I hope I'm pronouncing it right.
Yeah.
From Hungary.
Yeah.
So please, Gergo, please share your presentation.
Okay, thank you very much. Just a second. All right, can you see my screen now?
Yes, we can.
Okay, great. Thank you very much. Good afternoon, everyone. It's really honoring to be here today. My name is Gergo Igneczi from ISTRC21 University from Győr, Hungary. With two of my colleagues, we would like to present you a topic within the autonomous system development for vehicles, which is within the scope of multiple projects of the Vehicle Research Center of our university. And it's focusing mainly on motion control of these automated or autonomous vehicles. The exact title is the implementation of a self-developed model predictive control scheme for vehicle parking maneuvers. So this is basically a model predictive control that we have built up from scratch to get familiar with the structure and to get the main challenges for the upcoming months and years regarding this controller studies. And we also focused on special low-speed maneuvering, mainly used for parking maneuvers for these automated functions. So basically, this is our topic for today that I would like to present you in this couple of minutes. First, I would like to present to you the problem that we face. Then the exact structure of this model predictive control, how it is built up, what kind of equations and what kind of models we are using, how we implemented and validated this control scheme, what kind of results we achieved through the validation and testing, and how we would like to continue our topic. First of all, as I said, the problem formulation. So first of all, of course, there is a generic solution need for motion control of automated vehicles. This is just an illustration on the right side, the usual layered structure of these autonomous systems, focusing on mainly the trajectory planning and the subordinate components like vehicle level control, which is in the main focus of this presentation. Of course, there are some subordinate further control layers, inner loops that can be implemented in such an automated motion control system, like actuator control, or even below some really quick low-level control layers. But these last two ones are not scope of our study. So vehicle level control, in our aspect, means kind of a control of a vehicle as one single body. This is based on some measured values, feedback from vehicle sensors like pose in a given frame, velocity, yaw rate, and acceleration. The input of this vehicle level control is usually a reference value set, which is planned by a superposed planner. This is what I denoted as a trajectory planner. And the output of the controller is kind of a target value defined at the vehicle level. This can be either curvature, yaw rate, or acceleration, or any kind of kinematic target or desired values that can be realized by the actuators below this layer. And on the other hand, as I said before, there is this specific use case that we're targeting to accomplish. This is a parking maneuver, as illustrated on the right side now. This is a modeled maneuver, as you see, with a S-curve-like or S-curve shaped trajectory planned, and reaching a full stop destination at the end of the maneuver. Of course, our plan is to widen the number of use cases where this controller can operate, and this is only a reference use case that we're testing the controller for the first time. How the model predictive control structure is built up. So the combinational steps that we are implementing in nutshell, of course, there is a reference value set, which is coming from the previously mentioned planner. This is recalculated or resampled usually for the prediction horizon. This is fed into the controller directly. There is, of course, a measurement, or also can be comprehended with an observation or observator itself, measuring the output and state variables coming back from the plant itself or from the vehicle itself. There is an error calculation. The error calculation also considers, besides the reference value set and the fedback measurement results, a prediction based on the model that we're using for the controller. It's a weighted error calculation between the measurement and the model itself, which will yield an input set, and which can be fed into a predefined cost function. And the cost function can be optimized through the prediction and the control horizon, either unconstrained or a constrained way. The advantage of such model schemes is that these are extremely accurate at its operation range. But I bolded this letter phrase because it's really important to see that these models are really sensitive to the model accuracy. This is a kind of disadvantage of these models. Oh, sorry, of these controllers. However, this optimization can be done in runtime, even along constraints, which gives this extremely good accuracy in the end. It is able to handle multiple input, multiple output systems, which is another good advantage using those controllers. And it's quite straightforward and clear how to calibrate these controllers, which can make an application procedure much easier. And among the disadvantages, besides the sensitivity to the model accuracy, I have to mention that it's, of course, the computational capacity requirement is much higher than for linear or traditional controllers like PID controllers. Okay, really briefly, and going through just the main steps of the equations that we're using. Of course, we need kind of a state space model of the plant in a kind of a usual way. We usually build it up on a discrete time horizon or time domain. There is a differential model, of course, that can be formulated between different time steps. And this can be completed into an augmented model, which will be the basis of the model design in the end. For the prediction and the control horizon, the output vectors and the input increment vectors can be put into one compact model. This will be the kind of the new model, which can be rewritten in the as per the last line, as you see. And this will contain now all the values for the entire prediction time ahead that is calibrated. And this new model has this new system and input matrices per the second line on this slide for the prediction and the control horizon accordingly. The set of reference values must be always written also for the prediction horizon to be able to form the right predicted errors. And the k number of output can be formulated in a one column vector, and these column vectors into a bigger column vector for the prediction horizon. The const function is usually written in the following form, where the magnitude of the inputs and the error itself can be weighted accordingly. And if we rewrite this cost function, we can see that this can be formulated as a quadratic optimization problem that can be solved with different solvers. We used Hildreth's iterative approach, which gave us sufficient performance among the boundary conditions that we set up. How we implemented and what kind of model we used. So we, for this first test, we used the kinematic single track model, which is kind of easy to implement. The system inputs is the steering angle and the longitudinal acceleration. Therefore, both the longitudinal and the lateral kinematics can be controlled in one model, which is good. The system outputs are the lateral position compared to the reference line, the orientation error or the orientation itself, and the longitudinal velocity that we would like to control. The operational range, as I mentioned before, is mainly a lower speed range below 30 kilometers per hour. The steering angle was limited with a plus minus 0.5 radian angle, and the maximum acceleration and deceleration was also limited. The implementation was carried out in a Simulink environment, MATLAB Simulink environment, which is really good because it has this robot operating system toolbox. Therefore, the model itself could be compiled and built as a ROS node with the help of the Simulink coder, and therefore can be integrated into our entire autonomous chain that we built in ROS. The validation occurred in two steps. One step was kind of a concept validation with a kinematic model within still in Simulink before building the ROS node. And the second step was carried out with a dynamic model using this LGSVL simulation framework, where the environmental model and the entire dynamic model of the vehicle is present, and it's a much more real world-like modeling or simulation environment. Here are the first results that we achieved. You can see always two different lines or diagrams or graphs on the diagrams. One from the MATLAB. This is from the Simulink. This is the proof of concept simulation results, and the other one is the LGSVL simulation. Regarding the position or the path run by the vehicle during the maneuver, we can see that the kinematic model yielded almost ideal solution, while the dynamic model running in the LGSVL simulation environment led to a small overshoot and small errors, but still acceptable. The maximum velocity was 5 kilometers per hour. And this is good because the stable operation could be achieved for both simulations. The steering wheel angles were limited according to the constraints. And we have to mention on the steering angle signals, there are some deviations for the LGSVL simulation framework. This is this high frequency noise on the measured signal, and this is traced back to some communication issues between the real-time simulation environment, the ROS node, due to some capacity problem on the simulation computer. And of course, there is a terminal orientation error, which the logic currently doesn't consider, which can be seen on the next slide, this orientation control plot, where the same oscillation can be seen on the LGSVL curve. This is still something that we work on and we want to reveal. Of course, there are some other deviations between the dynamic and the kinematic simulations, but still there's a nonlinear ratio between the steering angle and the steering wheel angle in the simulation environment, which can only estimate it in a linear way right now. Therefore, it still has a lot of improvement potentials, I think, when we reveal these deviations and fix them. As for the longitudinal control, what we see is that the speed control is good in both cases. However, for the GeoSphere simulation around the stopping points, there are some stop and go toggling, which is also assumed to be a problem traced back to the communication problem between the simulation framework and the software itself. So what we would like to do in the future, in the upcoming months, hopefully to analyze and fix these previously mentioned problems. We have already started to fix those. During these days, we're working on it. We would like to, of course, extend the testing range of the controller to further stress test its limits and find the robustness robustness critical corner cases. And of course, we would like to take the entire software to real vehicle tests, which is also under preparation right now. And in the upcoming months, or even the entire year, we would like to carry out some researches in the model sensitivity of these model-based controllers, but because what we see is that this is a real critical problem or weak point of such controllers. This is somehow related to some stability analysis that we would like to also carry out in the near future. Later, we may transform the model from kinematic to dynamic, which will open up some further possibilities, hopefully, for higher speed ranges. And of course, we would like to do comparison between different control structures to have a full picture how MPC behaves compared to some easier or much simpler solutions. And we would like to reveal these differences and advantages. So I think, yeah, that was it. Thank you very much for your attention.